Hi everyone, welcome to the first video on Chapter 8, where we make the transition away from gases, and we're actually going to start looking at some other phases, including the liquid phase and the solid phase. And then in future chapters, next chapter for instance, we're going to be looking at mixtures and even solutions. And then the chapter after that, we'll get to electrolyte solutions and then go off from there. But for this chapter, we're mainly just going to be focusing on the solid and liquid phases of pure substances, which is going to make most calculations quite a bit simpler than they would be if we were dealing with mixtures. Let's start by answering the pre-class questions. Which of the following statements are true about this figure to the right? It turns out that this one is true, and also this one is true. Notice that number 1 and number 4 are kind of opposite statements to each other. However, it is possible that both of them could have been false if these were perfectly straight lines that we're looking at. But it turns out that number 4 is correct. And that's because we will see that as the temperature increases, even within a particular phase, the molar entropy is also increasing, and that mu is going to be proportional to negative molar entropy. So that means that this is going to create slightly downward curvature. So more on that later. I think that will make more sense once we finally get to it. But then let's look at this next one here, number 2. The slope of each line is given by the derivative of the chemical potential with respect to temperature at constant pressure equals the negative molar entropy. That is true. And we'll get to that one a little bit later. Then number 3, which we're saying is false, is the curvature of a chemical potential as a function of T is given by the derivative of the chemical potential with respect to pressure at constant T. This little sub-statement right here actually turns out to be true. However, what is not true is that the curvature of the chemical potential as a function of T is going to be the derivative with respect to T, not the derivative with respect to P, like it says here. By the way, this is a slight error. That's actually a positive right there. So I'm going to need to go back and fix that in the PowerPoint. Of course, feel free to post any of your questions on the discussion board. So here's what we're going to be covering over the course of the next few movies. We'll be discussing these two issues in the first video, the big question of this chapter, and the free energies of phase changes. And then in the second video, I'm planning on addressing just this point here. And then in the final video, I'm planning to address those 2 points right there. Okay, so to review a few things that we've mentioned in previous chapters, remember the phase refers to whether the substance is a solid, liquid, or gas. However, phase is not synonymous with state because there could be multiple phases for a given state. For instance, it is possible that for some substances, the solid state can have multiple phases. And it's even possible for the liquid state to have multiple phases, interestingly enough. And the example they give in the beginning of the chapter was liquid helium, which can have the normal liquid phase and also the superfluid phase. The second point, remember that the Gibbs free energy determines whether a process is spontaneous or not. Negative delta G's indicate that the process is spontaneous. Also, if the system has a choice of going to one state versus another state, it will choose to go to the state that has the lowest Gibbs free energy. The example we saw of this was the folding and unfolding of a protein. At different temperatures, the system had different Gibbs free energies, and it always chose the state that had the lowest possible Gibbs free energy. This will be an important concept a little bit later in this chapter. Okay, the third point, chemical potential of a particular substance A is the derivative of the Gibbs free energy of the system with respect to the number of moles of that substance at constant temperature, constant pressure, and constant other substances. However, when we're talking about a pure substance, the chemical potential is a lot easier because the chemical potential is just going to equal the molar Gibbs free energy. So that's the Gibbs free energy of the system divided by the number of moles. And so this can be a convenient way to think about the chemical potential if you're not still a little bit shaky on the concept and you're not really sure what it means. Start by thinking about, at least in this chapter, that it's just a molar Gibbs free energy. It gets more complicated in later chapters, but this can be a helpful way to think about it at this point. In the past couple of chapters, we've seen several different examples of equilibrium constants, pressure equilibrium constants, fugacity equilibrium constants, etc. And those tell us the relative proportions of the different substances within the system. It's going to be a little bit harder for us to think about Kp with the liquid and solid phases, but we'll get to those later and see how to think about those. Lastly, the book mentions the difference between a vapor and a gas. And the thing to keep in mind with this is that a vapor is a substance that's mostly in the liquid or solid state at room temperature. An example might be water. Water vapor exists above the liquid phase of water, but the water is predominantly in the liquid state at room temperature. In contrast, a gas, like nitrogen gas or oxygen gas, is mostly in its gaseous state at room temperature. And we're also holding the vapor and the gas at standard pressure. So here's the main question that we're going to answer in this chapter. We need to find out what phase the system is going to be in for a given temperature and pressure. And how can we relate this prediction to the thermodynamic quantities that we already know about, like entropy and Gibbs free energy? So this is the main question of this chapter. For a given material, at a given temperature and pressure, will it be a solid, liquid, or gas? And by the way, the mixture aspect applies mainly to next chapter. And the answer depends, of course, on the Gibbs free energy and the equilibrium constant for each of the different phases. And it's important to keep in mind, you should have a pretty good intuition about this at this point, that the entropy of the gas phase is higher than the entropy of the liquid phase, which is higher than the entropy of the solid phase. So to begin, we're going to write down the following formula, which no doubt looks fairly familiar to you by now. The formula for the Gibbs free energy, though we've made all of the extensive quantities into intensive molar quantities. And we're going to use this right now. By the way, that can also be written as mu, the chemical potential. I'm going to start by drawing a little plot where on this axis I have the temperature, and then on this axis I have the molar Gibbs free energy, or we might say the chemical potential. And then I can draw an approximately linear function here, because this intercept right there is going to be the delta HM, and then the slope is going to be negative delta SM for this line. And let's say, for the sake of argument, that this corresponds to the liquid phase of the system. Okay, so this is a plot of the molar Gibbs free energy of the liquid phase. So if we were to now plot a different phase, say the gas phase, we're going to have a slightly different line. And it's going to be a steeper line because the molar entropy of the gas phase is going to be a larger value. So there's delta GM of the gas, and it's going to have a different enthalpy as well. And I'm just sort of putting this line fairly arbitrarily at this point. And then we need our last phase, which is going to be the solid phase. And I'm just going to draw it like this. That's going to have the shallowest slope of all because the delta M, the entropy, is the smallest for the solid. And it's going to have a lower delta HM at this particular pressure. So, which of, I need to label this one, solid, right there. So, which phase is the system going to be in at a given temperature? Hopefully you recognize that the system is going to choose whichever phase has the lowest Gibbs free energy. So that means for this region right here, the system is going to choose this lowest Gibbs free energy, which is the solid phase. Then right here at this point, that is the freezing temperature, freezing point. Okay, so we could call that TF. And then right here, because this one has the lowest Gibbs free energy, the system is going to be in the liquid phase because that's the liquid curve. And right there, that's the boiling point. So we could say that's TB. And then for this high temperature region here, this curve has the lowest Gibbs free energy. So this is going to be in the gas phase. So this particular plot is a lot like what water would look like at 1 atmosphere, because it goes through a solid, liquid, or gas phase depending on the temperature. By the way, this plot up there is labeled slightly differently. They call that the melting point. Freezing point, melting point. It just depends on what state you're starting with and what state you're ending with. And in this case up here, they're assuming you're going from the solid to the liquid state, whereas it's also valid to call it the freezing point, because you might think of going from the liquid state to the solid state. And both of those transitions will happen at the same temperature.